All right. A minute. All right, welcome everyone. So we're going to talk really briefly about an introduction to x86 assembly. So quick introduction. This is Stephanie. My name is Chris. We've been doing cybersecurity research for about a decade. We also teach classes on assembly and computer architecture at The Ohio State University. And we do some workshops on assembly and reverse engineering. If you're interested in learning more, you can check out DazzleCatDuo for that information. But most importantly for this presentation, we're sort of x86 apologists. We think this is a really fascinating, complex architecture that everybody should know a little bit about. So that's sort of what this presentation is about, is a sort of brief introduction to this. Now, x86 is really, really complex. We can't cover everything in the next 25 minutes. So our goal today is sort of to start with zero knowledge. Maybe you know a little bit about assembly or x86, maybe you know a lot, maybe you know nothing. We're going to assume that everybody knows nothing, and we're going to try to get to the point where we can all write a hello world program, which I think will put everybody on good footing for learning a lot more if you're interested in pursuing this further. But the premise behind all of this sort of starts at a very, very low level. That's what assembly's all about. And the idea is that everything your CPU does ultimately comes down to digital logic, right? On and off, ultimately running current through transistors or not, which we abstract away as the idea of either 1 or 0. Now, if you think of these ones and zeros, the way a computer chip is designed is it's designed to accept a stream of these ones and zeros and basically do things based on a specific stream that you give it. And if you think about a stream of ones and zeros, essentially what you have is just a bunch of numbers that ultimately tell your CPU what to do. So we call those numbers machine code. And if you break those bits, those ones and zeros, into groups of 8 and change it into hexadecimal, you end up with something that looks like this. So this is what we would normally think of when we think of machine code, just a big stream of hexadecimal bytes. Now, ultimately, this is what your CPU is after, right? This is what tells the CPU what to do, when to do it, how to do it, etc. But humans don't think this way very, very well. We need some sort of abstraction around this. So whereas on the left is what your CPU wants, on the right is a way that's a little bit easier for us to think about that information. So on the right is what we call assembly. It's a light abstraction over machine code that makes things easier for us to read. So for example, I might want to tell the CPU, well, return from your current subroutine. So I can just remember that that's the ret instruction instead of having to remember that the machine code behind that is the number C3. And you can see that although assembly isn't the easiest thing to read, it's a whole lot easier to start making sense of than the machine code. So for example, even with just a little bit of knowledge here, we can sort of infer that, well, this first instruction pushes something onto the stack. This next one copies something from one value into another. Then we do some arithmetic, then we call a function, we leave the current stack frame, we return from this function. So you don't need to know exactly what each of these do, but you can sort of get a sense for what's going on at the machine code level if we can read this assembly abstraction of that information. So ultimately, as humans, it's more practical for us to write in assembly, but that lets us get about as close as we would ever want to get to communicating with the processor itself. So fortunately, we don't need to understand exactly how to do that translation between these two abstractions ourselves. If we want to write in assembly and we want to get that into a state that the CPU can understand, we can use a tool called an assembler in order to convert our assembly into machine code. On the other hand, if we want to go in the other direction, if we want to take machine code and bring it into something that we can understand, if we want to take that into assembly, we can use a disassembler in order to do that process. So now that we sort of understand the premise of what we're looking at, we need to pick a specific architecture, a specific assembly language to dive into in a little bit more depth. So let's look at x86. So a lot of people will shy away from x86. If you don't know a lot about assembly and you haven't really looked at a computer from this perspective before, a lot of people will tell you stay away from x86. That's not a good place to start. And the reason they'll say that is x86 is just insanely complex. So people will say it's not a good language to start with. And I actually don't think that's the case. I think x86 is the perfect language to begin learning if you're interested in diving into assembly. And the reason I say that is that with x86 you can build and run and play with the language on your own computer right now. You don't need special hardware. You don't need emulators. Basically, every one of you could pull out your laptops and start using this immediately. And I think that makes it a great learning tool. It's also extremely popular. It's present on billions of systems worldwide, has total market dominance in the PC space, which means that there's plenty of learning material. You can start diving into any of the applications on your computer right now and pulling them apart in order to learn more about how they work. And it forms the core of a lot of familiar operating systems, Windows, Mac, Linux, all sort of built in one way or another, or in one flavor or another on x86. So I think that makes it a really, really good language to start with, despite its complexity. But that's not to say it's not complex. It is. The Intel Software Developers Manual, what we call the SDM, is sort of the go-to reference for learning x86. You can find it here, but it is 4,000 pages long last time I checked, and it does not even begin to scratch the surface of all of x86. The reason I point this out is there's no way in a 25-minute presentation we can really get deep into this. So our goal moving forward is basically just to give you the basics, give you enough that you can get started if you want to go out on your own and dive in to some more depth. So with that, I'm going to hand things over, and Stephanie's going to talk about the actual technical aspects behind all of this.
All right, so x86 assembly. So we kind of introduced the topic. I'm going to introduce that there are two main rivals of x86 syntax. So despite x86 being a known architecture, there's actually no one way to write x86. It's actually dependent on what assembler you're using. So there are two of the largest competitors in the x86 syntax world, are what you'll see called AT&T syntax and Intel syntax. And both have pretty good market dominance. They both have their pros and cons. There are hundreds of smaller ones. For the purposes of this presentation and my own personal opinion, I think AT&T is horrible and hard to read. So it's the one on the top. And we will be focused on Intel. But if you're ever looking up x86 and you see all these weird like percent signs and dollar signs everywhere, you are looking at AT&T syntax. So make sure you just understand some of the small nuances. It's still x86 assembly, it's just a different syntax. If you don't see all the percent signs and dollar signs, you're probably looking at Intel syntax. So assembler syntax, I said it depends on your assembler. There is no one right way to write x86, which is different from most programming languages. It all depends what assembler you're using. So the assembler that is most commonly used, and the one I'll introduce, is called NASM. So NASM is a Linux-based net-wide assembler, it's called. So NASM syntax, it's Intel syntax. Lines don't end in a semicolon. Semicolons start a single line comment. So the last line there shows you instruction. And then colon would be a comment, otherwise a colon's not necessary. So some x86 instructions. So the first thing you need to understand before we show you instructions is how you use registers. So the registers are how your processor actually stores data on the processor. System memory is extremely slow, and extremely slow seems kind of odd to think of your system memory. Memory's fast, and it's gotten a lot faster, but compared to a register inside of the CPU, it is thousands of times slower to fetch something from memory than it is to fetch it from one of the CPU registers. So the registers are your preferred way of handling and manipulating data. If you can avoid memory fetches, you want to for speed reasons. Registers are actually inside the processor physically. That's why they are so much faster. So we're going to focus on the 32-bit registers. In this particular presentation, know that the 64-bit, everything we're learning here, it still applies to 64-bit registers. It's just that you put an R in front. So instead of EAX, it would be RAX. It's just a 64-bit version of the same register. Everything else still applies. So the naming convention for the 32-bit registers, you see that you really only have these 6 general purpose registers at the top. So EAX, EBX, ECX, EDX, ESI, and EDI. So the top 4, you can refer to smaller versions of them. So you see you can look at like AX as just the lower 16 bits of it. And that's because x86 has been around since the 60s and 70s. And it has been backwards compatible since then. So the current x86 manifestation is still backwards compatible with the original like 16 and 8-bit versions of the architecture. And that's why you have these old historical versions of these registers, because the original code written for the original 8086 and 8087 would still run on a modern processor. So the other instruction, or the other register worth knowing, is EIP. So this is your instruction pointer register. You have no direct control over this. You can't load it. You can't use it like a normal variable, but it always contains the memory address of the next instruction to execute. So anytime you're doing debugging, the EIP one is one you're going to want to pay attention to, and it's the next instruction. So not the one that's currently executing, but what will be next if you were to step through your code. The other important thing before we introduce actual instructions is how you actually access memory. The registers are the preferred way to do things, but routinely stuff is stored in memory, or you saw you really only have 6 registers. And for all the complex things your computer does, there's no way to do that entirely in those 6 registers. So you will routinely find needs where you have to store things in memory and refetch them. So if you're going to manipulate memory, you simply put the memory address inside of square brackets is how you're telling the CPU basically go to that memory address and fetch the information at that memory address. So Kristen mentioned that the developer manual for x86 is 4,000 pages. Truthfully, if you just learn the instructions that I show on this page, that is going to get you 95% of the way. Chris and I consider ourselves to be x86 experts, and I would guarantee if I looked through that developer manual, there'd be a ton of stuff that I didn't know, because the truth is you don't need it if you're doing x86. It's all really obscure corner case stuff. So these are the instructions you're going to want to focus on. I'll introduce most of them today, but when you're going back, or people watching this video, kind of look at this slide, and these are the instructions you should learn to be able to actually do x86. This is one of my favorite references. So if you're on your computer and actually trying to look up x86, this is the one I always go to for quickly looking up x86 instructions and quickly how they work and how they assemble. So the most important instruction is the move instruction. And despite being called move, it actually makes a copy. It does not move data. So the way it is move and then destination source. This is the biggest difference between Intel and AT&T syntax. AT&T has source and destination flipped. So if you're looking at AT&T syntax, everything is reverse order from Intel. So the Intel syntax is destination source. And then I've got examples down there, and I kind of have that part where it says copy underlined, because people when they're starting get very confused by the fact that it's called move. If I am moving from, say, memory address 100 into EDX register, that original data value still stays at memory address 100. It is not an actual move, it is a copy. Same for the last one. So if I'm moving from the EAX register into the EDX register, EAX still maintains its original value. I've simply made a copy of it. So it's called move, but it's actually a copy instruction. So add and subtract. So for Intel, just ubiquitously, it will always be destination first, and then whatever other value that instruction needs. So if I'm adding something, I have destination and value. So the interesting things about add and subtract is there's only 2 arguments. So your destination is always one of the arguments. So if I'm adding add EAX and then this long number, EAX is both used in the equation and is the destination. So your destination is always part of the equation. You can't save it in a third variable. So it's important to understand you're also overwriting one of your variables when you're doing an add or subtract. So the jump instruction, x86, like all coding languages, executes linearly, so it'll just keep going unless you hit something that will change or divert the EIP register. You cannot affect the EIP register directly, so the way you affect it is things like jump instructions. Jump will load the address that you have there into EIP so that the next instruction will be that instruction instead of the one that was after it. So in this case, jump begin, I'm telling it that the next instruction I want you to go to is a place that I've labeled in my code called begin. So an example of this to implement a loop. So real quickly, I move a 0 into EAX, so I'm setting using EAX kind of as my loop counter. I'm going to increment EAX, which just adds 1 to EAX. So on first increment, it would be a 1. And then I'm going to jump loop. So that just loads the loop instruction, the address, which was 1 line ahead, into EIP. So the next instruction would go back up and increment EAX. So this is actually an infinite loop. EAX will indefinitely increment. I'll show you how to not have an infinite loop later, but just introduce the jump instruction. In this case, it's what we call an unconditional jump. It will always take the jump, which sometimes you need, but sometimes you need some that are conditional. To have a conditional jump, you have to do some kind of a comparison. So I have to have some kind of a statement that I'm trying to say, well, if this, then jump. If not this, then don't jump. So I do that by using things like comparisons. So the compare operator subtracts the second operand from the first operand. The results are discarded. So what I mean is if I compare a 5 to a 3, 5 minus 3 is 2. The 2 is discarded. That doesn't overwrite any of the operands, but the fact that it was a positive 2 is used in the next instruction to decide whether or not you are going to take that jump. So here's an example of it. So why is this useful? So if I load 100 into EAX, a 200 into EBX, and do a compare between the two, what that's actually doing behind the scenes is EAX minus EBX. So I'm going to get a 100 hex, a negative 100 hex. And what that's actually going to do behind the scenes is basically just set the knowledge that the information was negative. So if the result was negative, you get this SF, which is the sign flag. But all that's relevant to you is that the computer now knows that the result was negative, which meant that EAX is smaller than EBX. That's really all you have to understand. So reverse opposite of that. So now EAX is bigger than EBX. So if I load a 300 into EAX, a 200 into EBX, and do the compare, it's still going to do the 300 minus the 200, but this time I get a positive number. The fact that it's a positive 100 is irrelevant. All the computer cares about is that it was a positive result, which meant EAX was bigger than EAX. So that knowledge is what the computer is then going to use when you do then conditional jumps. So how do I do a conditional jump? So conditional jumps take into consideration the state of the CPU. So the CPU is tracking the fact that the last compare resulted in a positive number. So it meant greater than. So I get all these different possible control flow instructions. So jump equal. If the last compare, the numbers were equal, then jump equal would get taken. Jump not equal is the exact opposite. So you also have your jump 0, jump greater than equal to, less than, and less than equal to. So you can just kind of imagine the truth table with that compare instruction of if the numbers were less than, if they were equal, if they were greater than. I would use the various conditional jumps based on what I was trying to achieve. Remember, this is a 25-minute intro, so jumps are kind of complicated, but this is the basic to the logic you need to be able to make code that is not stuck in an infinite loop and does something conditionally. So here, a different example of how I could have done a loop. So I compare EAX to EBX, and then jump less than equal to done. So in that case, I'm comparing something, and if it is greater than, I want to keep executing. But if not, then I'm going to say, well, if it's less than or equal to, I'm done. I'm exiting my loop. So that's how you would do the equivalent of what you would think of as a conditional loop in any other language. So here's one. I want to loop from 0 to 5. So instead of incrementing EAX indefinitely, I only want to increment it 5 times. So load a 0 into EAX by a 0 moving into EAX. I'm going to increment EAX. I'm going to compare EAX to 5. And if it's jump less than or equal to loop. So if EAX was less than or equal to 5, I jump back up and do the loop again. So what that means is when EAX is greater than 5, I will not take the jump and I will end the loop. So now I've got the ability to do conditional looping. So different conditional. This one, it's not a loop. Now I have an if statement. So think of if statements in any other higher level language. If A is equal to B, I want to set some values. In this case, X equals to 1. So I'm going to say compare AX to BX, which is taking AX minus BX. And then if it's jump not equal to skip. So if they were not equal, then I want to jump over the next instruction. So you see how the skip label is lower. So if they were not equal, I'm going to skip the next instruction. If they were equal to, I will go ahead and execute the next instruction, which moved a 1 into CX. So in that case, now I can do things like if, else statements, else ifs. Using the compare and conditional jumps. So functions are another big thing you're going to want to be able to do. So think of call as the way that I invoke a function. So I would call and then the name of my function. In any higher level language, you would still put the name of the function just without the keyword call. This time you just have to add a call in front of it. Ret is how you return from one of your calls. So once you're inside of a function, if you're done with that function and you want to go back to where it was initially called, use the ret instruction. So no-op is a particularly popular one in the security field. So no-op or nop literally does nothing. It wastes 1 CPU cycle. It's often used nefariously for things like nop sleds and nopping out security checks. So if there's a piece of code that I don't actually want to run for security reasons, say I'm trying to get past your authentication, just fill it with nops, which is a machine code 90. The legitimate uses for it are for timing, trying to get code to be aligned. So it literally just tells the computer to do nothing, but it does it in a valid way that won't cause any crashes. So nops can be useful in the right situations. This example, I'm not going to go through it line by line, but I wanted it to be in here, so if you go back and reference the video, you can have some code. But in a 25-minute talk, I can't actually go over the whole thing. But here's an example that will actually show you just kind of how you would take a piece of pseudocode, in this case, some really simple addition and setting up of variables, and actually do some simple arithmetic on it. So that example is there for you guys to reference later. So the other important thing I want to introduce is the fact that you will need the operating system's help if you are writing x86. While it is true that you could literally do everything by writing at x86, if you wanted to turn on or off a pixel on your screen in pure x86, you're going to be writing thousands, if not tens of thousands of lines of code. It is not fun. So there are times when you actually want to ask the operating system to help you a little bit, even though you're writing in x86 assembly. So in Linux, we do that through what are called syscalls or int80s. So syscalls ask the Linux kernel to help you out. Say, Linux kernel, can you actually do a basic piece of functionality for me? So I'm going to introduce the two that we need for Hello World, but I've given you the links here to look at other system calls that you can easily invoke from x86 assembly to ask the Linux kernel to do things for you. So the first one you need to know is a syswrite. When we're writing Hello World, if I actually try to write the text Hello World to the screen, I could do it in pure assembly, but we're talking tens of thousands of lines. That one maybe hundreds of thousands. So I'd rather ask the operating system to help me out using a syswrite. The way you do that is you have to preload particular values into the appropriate registers and then invoke the operating system. So for a syswrite, I have to get a 4 into EAX. That's how I tell the Linux kernel that I want a syswrite. It's function number 4. In the EBX, I put a 1, which is telling it to write out to the console. So this will write out to a terminal. In ECX, I'm going to put the string I want it to write. And in EDX, I put the length of the string. So an example of that would write out to the thing. And then the int x80 is the thing that says, all right, Linux kernel, do what I just asked you to. So an int 80 is how you actually invoke the kernel. The sysexit is the other one. So if you want to actually exit cleanly from your application, you don't want your assembly to just stop. You want to tell the kernel, hey, I'm actually done, clean up this process. So at sysexit is how you do that. So putting it all together, I won't go through this in detail, but again, this is here for the video. So if you are going to start writing x86 assembly, this is how you will want to set up your file. Everything you see in black are keywords that you actually need to have in your file. And then where you see code goes here, variables go there. That's where you would put your code. That's where you would put your variables. This is just showing you examples of how you declare variables. So how you would declare ints, strings, anything that you might need in your code. Then putting it all together. So this is how you're going to actually build x86 assembly in Linux. So I told you we were going to use NASM, so you're going to invoke it with that first line there, NASM felf. Felf is telling you elf is the executable format for Linux, so you are saying build me something that can execute in Linux. And then linking it together is how you actually then link it so the operating system knows how to find all of the calls it was using, and then the dot slash is how you would run any executable. So that's just putting it in more detail. What NASM is doing with that command. The linker, you are telling it to link this with x86. That's what the melf i386 is doing. If you want to disassemble it, so you want to see what you actually built, object dump is built into all Linux distributions. So you will do the -d to tell it to dump the code and data section, and -mintel tells it to dump it in Intel syntax, because none of these tools agree with each other. So object dump defaults to AT&T syntax, NASM defaults to Intel syntax, so you need the mintel. You can throw this all in a make file, so here's a sample make file, so you don't have to type that out every time. If you do these -gs, we'll add debug symbols into your x86, so if you are writing assembly to debug it yourself to learn better, put the -gs, and that'll leave the debug symbols so it's easier for you to look at what got actually built. And then here is a Hello World application, so when you get home, pull up this video, or take a screenshot really quick. And if you write this into a NASM file, build it with the NASM and link it, this will actually print Hello World to the screen.
So that's sort of wrapping it up, a really quick crash course into x86. I think a lot of people want to know, like, where do I go now? Yeah, can you turn that down? where do I go from here? One thing I find when a lot of people are starting out with low-level assembly is they don't really appreciate the power of it and what you can do with it. The fact is, like, x86 is Turing complete. It's as powerful as any other programming language that we might use at a much higher level. We can do anything in x86 that we could in any other language. And sort of as a way of pointing that out, since I'm a 90s kid, I spent a lot of time playing Roller Coaster Tycoon. This game was written in 99% directly in x86 assembly. It made hundreds of millions of dollars. So it's a kind of a jumping off point. I think the best way to learn more is to basically just start with the building blocks that we discussed today and start trying to add your own additions. Just start using it to build tiny programs, start tearing apart other people's programs, see how they work. That's sort of the way to improve your knowledge of this. And again, like I said, sort of the sky's the limit with what you can do with this. So I hope this has been helpful, and we're out of time now. But thank you everybody for attending.